I guess we can get started if you're ready. Okay, great. So today we'll cover pipelining. We'll start pipelining, actually, finish microprogramming very quickly, and then move on. Well, I guess before that, there's an announcement. We're moving the Friday recitation session to 3:30 p.m. I think that was the general consensus from the class. And again, these are not required, but recitation sessions are there for, to help you. So you can go to any recitation session. But the feedback was 6:30 p.m. was too late. And we may move the Tuesday recitation session too. OK, so this is where we are. We've covered single cycle and multi-cycle, microprogrammed microarchitectures. We'll do pipelining today. And we may start some of the issues in pipelining, especially data dependence and control dependence handling. And then you know what's coming next. So hopefully we'll be done with control and data dependence handling by the end of next week. And then we'll start out-of-order execution the week after. Recap of last lecture. Again, just to warm up your caches. We talked about multi-cycle and microprogrammed microarchitectures. We talked about the benefits versus the design principles. You should remember the 3 design principles that we have. When do you generate control signals? We talked about what's a good idea, what's a bad idea. I gave you a bad clock cycle when you generate the control signals at the beginning of the clock cycle, the control signals that you need in that cycle. You don't want to do that. We talked about microprogram control, which is a really elegant way of designing a machine, a multi-cycle machine. Microinstruction, microsequencer, and the control store, which comprise the microprogram control. We talked about the LC3B state machine, Datapath, and the control structure. And we did an exercise in multiprogramming where we went through 4 states and we filled the microcode for those 4 states. And you're going to do many, many more states. We talked about other issues related, variable latency memory, how you handle that in a microprogram machine, alignment of memory. You'll need to do that when you actually do load word or load byte, one of those instructions that we gave you. And memory mapped I/O, how do you actually handle that in a real design? And then we circled back and talked about what's the benefit of microprogramming. It gives the hardware designer power of abstraction, right? It's a new abstraction layer. You can now program the control logic, if you will, control signals. And I'll start with the advantages. And one advantage was the update of machine behavior. So this is what we covered, basically. This is the simple LC3B control and data path that's microprogrammed. How many of you have read Appendix C, where this figure is from? No one? Oh, I see no hands. I guess Rachata is raising his hand. He's read it many times. Well, hopefully you'll read it, because this is important. There will be questions related to this on your homework and exam. You can definitely get, I'll guarantee that there will be one question about the microprogram control on the first exam and the final. About that, I give you the questions now. So you have no excuse to not get 100 in the exam now. Just kidding. OK, so this is the microprogram control structure. This is the microinstruction that's latched at the end of a cycle. This is the control store that stores the microinstructions for each state. And this is the microsequencer that determines the address of the next state, which is the next microinstruction. So this is a very simple design of the control structure if you look at it. And you can expand it, right? You can design a more complicated microsequencer, extend the number of states in the control store. Now, Intel won't tell you how many control store entries they have, but they have a lot of control store entries in their microcode. And this is the simple data path, actually. This is a single bus data path that implements the LC3B ISA. And with this microprogram control, the simple data path can become very powerful. You can do a lot of things. In fact, in your homework, you're going to do a lot of things with this data path. You may need to add some things to the data path. So the beauty of microprogramming is it gives a level of abstraction to the hardware designer, which is microprogramming. The designer now can translate any desired operation to a sequence of microinstructions. And we've covered this, so I'm going to go through this very quickly. All you need to provide to be able to do this is the sequence of microinstructions that's needed to implement the desired operation, repeat MOVS, for example, and the ability for the control logic to correctly sequence through those microinstructions, which is the microsequencer, and any additional data path elements and control signals needed. If you don't need any control signals to implement these operations or any new data path elements, that's great. You can translate a new instruction. You can implement a new instruction on the data path. Right. Now in your homework, you will need to add some data path element and control signals, I believe, to support repeat moves. You need at least some counters to count the number of things that you've moved, right, copied. Okay, this is another review slide very quickly. The advantages of this kind of control is now you can have a very simple data path and do really powerful things with it using the sequencer. You can translate the high-level ISA to microcode, sequence of microinstructions. And you can think of this as a user-invisible ISA, as we said. And we talked about some machines that actually made it user-visible, right? The Burroughs 1700, which is a really nice machine. I gave you the reference to it in the first lecture, I think, or maybe the second lecture when we talked about the ISA, which was a bit-addressable machine. You could basically update the microcode dynamically while the system is running. You didn't even need to turn off the system to update the microcode. So you could do really fancy, funky things with it, which is a lot of fun. You cannot do it on today's systems. Unfortunately, you don't have that visibility into the microcode. You could think of it as a good thing, because there are security issues. You may want to think about the security issues. What if someone updates your microcode, right? Well, while the program is running. That may not be a good idea. But you can do a lot of powerful things if you have once you have microcode. It enables easy extensibility of the ISA. You can support new instruction by changing the microcode, and can support complex instructions, a sequence of simple microinstructions. Enables the update of machine behavior. This is what I just talked about, actually. In fact, this is used today to fix buggy implementations. If you have a buggy implementation of an instruction, you can potentially fix it by changing the microcode in the field. You can have microcode updates. So I'll wrap up microprogram control before, and then move on to pipelining. There are very few things that we haven't covered, but these are important to cover. One is horizontal versus vertical microcode. Basically, what I've described in the last lecture is a horizontal microcode. We had a single control store. And this is actually a picture from Patterson and Hennessy Appendix D, which is the MIPS microprogram design. It's kind of similar to what we've seen, but it's not. I mean, it's much, much simpler. It doesn't have the state machine that's as complicated as what we've seen. But it does have more complexity. It has an adder to determine the next address of the microinstruction. So you can think of this as a microprogram counter, right? That's the address of the next microinstruction. Normally you go sequentially. Otherwise, if you need to branch within the microcontrol store, microcode store, you figure out the address over here. Basically, there's a microsequencer somewhere over here, which is the address select logic over here. But basically, this is a control store, as we've seen. And it provides the control signals directly. It's a single-level control store. That's called horizontal microcode. If you run into this term, that's what it means. You have a single control store. But this is not the only way to design the machine. I'm not going to go over this in detail, but you can think about breaking this control store into two control stores that look like this. Right? In fact, this is interesting. People have considered this. Actually, the paper that first proposed this was written in Micro 1978 by Skip Stritter and Nick Tredenik. And they basically showed in that paper that if you break up this control store into two control stores, the first control store specifies abstract operations. It doesn't specify directly the control signals, but it specifies register transfer level operations. For example, this line in the control store tells you PC should get PC plus 4. Make sense? And the second control store, you index the second control store with these abstract operations to get the eventual control signals. Now you get vertical microcode. It's a two-level control store. Make sense? So to get to the control signals, you need to do two control store accesses. And the first one provides you with abstract operations. The upside of this is if you're actually designing this carefully, because many microinstructions share similar abstract operations, you can make these two control stores simpler, smaller in size. And when the early machines were designed in the 1970s with microprogram control, the size of the control store was an important thing, because you were very much area limited. We couldn't put, I guess, 6 billion transistors on a chip at that time. You could put maybe 4,000 or so. And the size of this is very limited. As a result, you would like to minimize the size. By using two control stores, two ROMs, you can actually have a much smaller control store than this one. And the paper that was published in Micro is one of the major conferences in computer architecture, Microarchitecture, proposed this structure. And in fact, it was selected as one of the best papers that was published in the first 25 years of Micro, because it had a lot of impact on industry by doing this at that time. It's pretty interesting, right? I'm not going to go into this in detail, but you can think of how you can minimize these two ROMs compared to one ROM. In fact, existing processors may be doing something like this. If you read the patents, maybe you'll figure out. OK. There are also two other things related to microcode, nanocode and millicode. These are actually forms of microcode at different abstraction levels. Nanocode is a level below traditional microcode. Basically, you can provide microprogram control for a subsystem. Instead of the entire data path, you can say, oh, this is my floating point unit, let's say, and I have microprogram control in that unit. And your main microcode can call this nanocode to actually start operations of the floating point unit. I'll have a picture for this. Millicode is a level above traditional microcode. Basically, this is higher level ISA routines that can be called by the microcontroller to handle complicated tasks, like interrupt servicing, for example. So the microcontroller, the microsequencer, can call an ISA level routine to actually handle system functions. And this is a paper that I mentioned earlier, Millicode and an IBM Z-series processor that talks about how to do that. I'm not going to go over this in detail. You don't need to know this in detail. Just know the concepts. Basically, in both cases, why do we have this? Why do we want to have nanocode, a separate lower-level microprogram control for a subunit? Well, you don't want to complicate the main microcontroller. That's the main reason. You can think of these as microcode at different levels of abstraction. So let me give you one example. Let's say you have an FPU, just a floating point unit. It has some data path, and the control logic can be just microprogrammed, right? Just like what we've discussed. So you can actually microprogram the floating point unit operation. If you're doing add, you go through some microinstructions. If you're doing a multiply, you go through some other microinstructions, ... And this could be called from the microcoded processor implementation, right? Basically, when you get a floating point operation, floating point add, you actually start this microcontroller over here in the floating point unit, right? This way, you don't need to support all of those microinstructions inside the main processor. You kind of have a more modular design, right? That's what this nanocode enables. So this is called nanocode with respect to the microcode over here. Does that make sense? It's pretty simple concept. But in the end, from the point of view of this particular data path, it's really microcode, right? OK. So one last thing. Any ISA can be implemented with a microprogrammed microarchitecture. It's kind of obvious. We've looked at LC3B, but the book Patterson and Hennessy Appendix D talks about microprogrammed MIPS design. In my opinion, it's not as elegant as what we've discussed. But you could use that actually for your lab if you want. And we will not cover this in class, so you can do this for extra credit assignment. And this is the state machine that they propose. It has fewer states, but it's also harder to transition between the states. And again, I'm not going to go through this. And this is the control logic, control store. And I guess this doesn't have the micro. And this is the microsequencer over here. The microsequencer operates this way. Make sense? So you can take a look at this Appendix D. Once you're done with your assignment, you can actually use this to do the extra credit assignment, if you would like. OK. Well, let's wrap up the multi-cycle architectures. We've talked about multi-cycle architectures in the last lecture and very briefly right now. And their advantages and disadvantages compared to single-cycle microarchitectures. And we've covered actually all of this in the lecture, so I'm not going to do that. But you should be very familiar with this right now. We've also talked about microprogrammed versus hardwired controls and their advantages and disadvantages to each of those. And you should be very familiar with this right now also. Right? So if I ask you questions, you can answer. Since I know that you can answer, I'm not going to ask right now. OK. By the way, there's advantages and disadvantages. That's one of the most important things in this course, I think. There are advantages and disadvantages to every single idea you can come up with. There's no idea in the world that doesn't have a disadvantage. And there's no idea in this world that doesn't have an advantage. So I'd encourage you to think about all ideas that way. OK, so can we do better? We should always strive for better, right? We've designed a much better microarchitecture with the multi-cycle or microprogrammed architecture. Is there a limitation in this design? What is missing, you think? Are we utilizing the hardware that we have efficiently? Any thoughts? You guys are quiet today. Yes?
I guess maybe if you're doing like a memory access, you're using all the hardware that's kind of the memory access area, but there's all that other hardware that's doing nothing.
That's right, absolutely. Basically, we're not really utilizing the hardware efficiently, you're saying. If you look at, this time it worked. That's good. if you look at this, when you're doing a memory operation, when you're doing a memory access, only this part of the data path is being used, right? Whereas there's a lot of stuff that's in the data path that's not being used at all. We're basically gating off the signal such that no harm is done during that time. As a result, what we have is limited concurrency, right? We could actually use that part of the data path for other things. Well, what are those other things? Basically, you remember this instruction processing cycle where we have 6 phases, right? Fetch instruction, decode instruction, evaluate address, access operands, execute, and store result. Well, some hardware resources are idle during different phases. So when you're fetching an instruction, you're actually utilizing the memory, maybe the PC. When you're executing, you're just utilizing the adder, and everything else is idle. So fetch logic is idle when an instruction is being decoded or executed. And most of the data path is idle when a memory access is happening. So can we actually use this idle hardware to improve concurrency? And what would be the goal of this? Basically, if you have more concurrency, if you can do more stuff in that hardware, you can have a higher instruction throughput, right? So when one instruction is accessing memory, perhaps you could be fetching some other instruction, right, by overlapping these different stages of the instruction execution cycle. As a result, you can complete more work in one cycle. So the idea is actually very simple. When an instruction is using some of its resources in its processing phase, whatever phase it is in, process some other instructions on the idle resources that are not needed by that instruction. For example, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode the next instruction. When an instruction is accessing data memory, execute the next instruction. And when an instruction is writing its result into the register file, access data memory for the next instruction. This way we're basically pipelining the operation of instructions, right? Every instruction is doing something at different parts of the hardware. And that's the idea of pipelining. Basically, more systematically, pipeline the execution of multiple instructions. And this is analogous to many things that you see in life, perhaps. For example, basically, we're doing assembly line processing of instructions, right? You know about the factory assembly lines. You have a pipeline, basically, and different components go through different stages, and a car gets built. You don't start with a car at the beginning, but you start with some raw components that go through pipeline, right? That's the basic idea. Divide the processing cycle of the instruction into distinct stages of processing. And ensure that, of course, we need to ensure that there are enough hardware resources to process one instruction in each stage, right? And we'll see that soon. And we would like to process a different instruction in each stage, right? That's how you get more concurrency. Because when you're executing the instruction, you cannot also do the memory access for the same instruction. You need to get the concurrence from somewhere, and that's coming from a different instruction. And instructions consecutive in program order are processed in consecutive stages. The benefit of this is it increases instruction processing throughput. Now, instead of processing one instruction in a given cycle, you're processing multiple instructions in a given cycle, right? Basically, you're really you can think of instruction processing throughput as IPC, instructions per cycle. You're basically increasing instructions per cycle, right? If you think about a multi-cycle design, you're really completing one instruction every n cycles, where n is your CPI, right? With a pipeline design, hopefully, you're completing one instruction every cycle, assuming you can pipeline everything really nicely, right? Basically, you can make your instruction processing throughput 1 per cycle if you have a perfect pipeline. As I said, there is a downside to every single idea. And there must be a downside to this also. So I'd like you to start thinking about this. Can anybody guess what the downside is? Yes?
That giant bus doesn't work.
That's right, yeah. So you need more hardware cost, basically. Maybe giant bus is one example, but maybe there are other things that may not work also, right? You may need some additional registers or latches, as we will see. So it comes at a cost. So this is a pictorial view of it, if you look at this. Let's assume that your add, we have an add. It takes 4 cycles per instruction, and we have 4 independent adds. If you have a multi-cycle machine, what happens in that multi-cycle machine is you first fetch, decode, execute, and write back the first add. And then you fetch the next add only after the first add finishes. And then fetch the next add only after the second add finishes, and so on. So it takes 16 cycles to execute 4 adds. basically 4 cycles per instruction. Whereas if you have a pipeline machine, this is the convention I will use in some of the lectures. This is time on the x-axis. It's the first cycle, you fetch the first add. In the next cycle, the add moves to the decode stage, and you fetch the second add. In the next cycle, the first add moves to the execute stage, the second add moves to the decode stage, and you fetch the third add. In the next cycle, the first add moves to the write back stage, the second one in the execute stage, the third one in the decode stage, and you fetch the fourth add, so on. At this point, your pipeline is full, basically. You have a 4-stage pipeline, and you have 4 instructions at this time unit. So if you look at this, what you're really doing is, in the steady state, when your pipeline is full, you're really completing 1 instruction per cycle. Does that make sense? I mean, if you just look at 4 adds, of course, you're completing 1, 2, 3, 4, 7. You're completing the 4 adds in 7 cycles. But assuming you have adds coming in, what your execution will look like in the steady state is a replication of this particular column over here. Right? As a result, you'd be completing 1 instruction per cycle. It's kind of beautiful, right? OK. Of course, life is not as beautiful as this always. I've given you the best case scenario for pipelining, basically, right? And we'll see there are many, many not so best case scenarios. In this case, for example, the adds are all independent, right? What if they were dependent? Some of them were dependent. What if some of the instructions took much longer to execute, right? What if you had branches? Well, when you're fetching the branch, you don't even know if it's a branch, but then you need to fetch the next instruction. What do you do? Right? So these are the problems with pipelining that we will cover a lot. So life is not always this beautiful, but let's take a look at the beautiful life first. Because that's how you get hope and then fix the problems with the non-beautiful parts of life, right? OK, so there's a good analogy for this. This is the laundry analogy from the book. Basically, you can do laundry this way, right? You have a lot of laundry because you're all students. You leave your laundry until the last minute, until you have no clothes left. I'm like that too, actually. Everybody's a student in the world. And as a result, everything piles up, and you have 4 different loads of laundry in the end. And this is exactly how you do laundry in real life, right? First, you place 1 dirty load of clothes in the washer, and when the washer is finished, place the wet load in the dryer over here. When the dryer is finished, take out the dry load and fold. When folding is finished, put the clothes away, or ask your roommate to do it because you don't like that job for some reason. And only after that, you take the next load and put it into the washer, right? Everybody does that, right? I hope not. Because this makes no sense, because you would be sitting in front of the laundry machines for a long time if you do that. Basically, to do 4 loads, and you start at 6 p.m., and you would be up until 2 a.m., assuming each of these steps takes 30 minutes. Right? That's a bad idea. That's a multi-cycle design, basically. Right? You do your laundry, each load serially. So if you look at the steps to do a load are sequentially dependent. So you cannot just dry the load, wash the load. Well, this is a dryer, right? This looks like a dryer. You cannot just dry the load before you wash it, right? Otherwise, there's no point in doing laundry. So these are all sequentially dependent. But there's no dependence between the different loads. So you can exploit this to be more intelligent or save time, I guess. And different steps do not share resources. If you look at this, dryer is separate from the washer, and folding is separate from whatever this is, putting the clothes away. So a much more intelligent way of doing laundry, which I hope all of you are doing, if you have more than 1 load, is this. You have 4 loads of laundry, and you pipeline. When the first load is finished in the washer, you move it to the dryer. And at the same time, you actually load the washer with the next load. You can actually do these things in parallel. You have 2 hands, right? You have enough resources to do that, actually. So there doesn't need to be a lot of switching overhead between. But think about the switching overhead. It may not be perfectly pipelined, actually. Basically, this way, you can increase throughput by 4, right? Basically, you're actually finishing 1 load every half hour once you're at the steady state. And you don't need any additional resources. And latency per load is the same. This is critical. So to finish 1 load, you still take 2 hours. 2 hours, 2 hours, 2 hours, 2 hours, from the beginning to the end. But the total latency of all of the loads, it's much smaller right now because you're done at 9:30 p.m., right? Not at 2 a.m. So the pipelining improves overall execution time, but it doesn't reduce the overall latency of an operation, of a single load. In fact, it may increase the overall latency of a single load because you now have switching overhead, potentially, if you cannot hide that overhead. OK? So this is a nice analogy, I think. And it works, actually, if you change things. So these damn dryers are always slow for some reason. Is that your experience also? Yes. For some reason, the people don't make these dryers fast. I don't know why. But let me take your question after this. If the dryer is taking 1 hour instead of 30 minutes, well, you have a problem, right? This is the multi-cycle machine. Let's ignore that. But this is your pipeline. Now your pipeline is not that great because the slowest stage decides your throughput. You're not, let's say this is taking 1 hour. What's happening is you do not complete a load every half hour now. You really complete a load every 1 hour. So the slowest stage really decides your throughput. That's your bottleneck stage in this case. Well, how can you solve this problem? You still want to complete one load every half an hour. What do you do? More dryers, yes. Dryer A and dryer B. Right? Have one more dryer. If something is taking very long, you can have more of those things. And assuming that you have more loads, you can actually use those different things. Make sense? So the first load uses dryer A, the second load uses dryer B. That way you can restore the throughput. You still can finish one load every half hour or 2 loads per hour using the 2 dryers. Well, the pipeline is exactly the same. If one of the operations multiplies taking 6 cycles, and that's your bottleneck, have more multipliers. Another alternative to this would have been pipelining the dryer. But that doesn't work, I guess, right? You can think about it, right? You could actually have half of the dryer to something and half of the dryer to some other thing, but then you need to design the dryer in a different way. Make sense? OK. So if you look at a multiplier, you can actually pipeline the multiplier. You can actually make it take still 6 cycles, but you can start one operation every cycle. And you can have 6 stages in the multiplier. Okay? That's very hard to do in the dryer case, I think. OK. So let's talk about an ideal pipeline. I think I'll switch back to this because we don't need it for a while. So our goal, remember, was to increase throughput with little increase in cost. Always, cost is always important, as we discussed in the last lecture. You want to always minimize cost as long as you're satisfying a design point. In this case, it's the hardware cost. So what do we need for an ideal pipeline? If you look at this previous thing that we discussed with the independent loads, first of all, we want to repeat identical operations over and over. If we repeat the same operation on a large number of different inputs, then you can get close to an ideal pipeline. Basically, all laundry loads go through the same steps, exactly the same steps. Whenever you do laundry, you don't skip the drying step. Right? There has to be some drying step. You need to repeat independent operations. No dependencies between repeated operations. Basically, different loads are not dependent on each other. Right? You finish the first box, and then you move to the next box. And uniformly partitionable sub-operations. I guess it's a mouthful. But basically, what this says is processing can be evenly divided into uniform latency sub-operations that do not share resources. If you look at the previous load example, we can uniformly divide everything to 30-minute chunks, right? And everything takes 30 minutes, exactly. And once someone violates that, you need to do something special. When someone takes 1 hour, then you need to do something special to maximize your throughput, right? So an ideal pipeline works this way. If you have identical operations, independent operations, and uniformly partitionable sub-operations. We will see later if an instruction pipeline is this way. So an automobile assembly line kind of looks like an ideal pipeline, assuming you can satisfy this last property, right? Assuming each component somehow has the same throughput, if you will. Doing laundry is kind of like that, too. What about the instruction processing cycle? Well, we'll look at it. The reason I say automobile assembly line has identical operations and independent operations is different cars have no dependency on each other, right? You assemble one car, the next car is totally independent. And all of the cars go through the same steps, assuming it's the same car or same model, right? You just need to guarantee this one. Whereas in the instruction pipeline, it'll be very different. Some instructions are dependent on other instructions, right? So it's not a perfect pipeline in that sense. Make sense? You still have your question?
Yes, when you said increases throughput by 4, you mean like by 4 times, right?
That's right, yes, by 4 times. Okay. Okay, so ideal pipelining. Let's assume that this is kind of the notation I will use in some of the lectures, but this is fetch, decode. Well, I guess I should do this. Yes. Fetch, decode, execute, memory access, write back. Assume that all of this takes t picoseconds, and this is a multi-cycle design. In a multi-cycle design, your throughput is 1 over t, right? Approximately. I say approximately because there may be some delays over here, right? If you want to have an ideal pipeline, you divide this into 2 stages. That's a 2-stage pipeline, and ensure that each of them take t over 2 picoseconds. As a result, your pipelining throughput increases to 2 over t, doubles, right? And if you want to divide into 3 stages, this is what you do, basically. Each stage takes t over 3 picoseconds, and you divide it in some way. And as a result, your throughput triples. That's nice, right? Ideally, that's what you would like to achieve, but that's not what you get in real life, right? Because these things that you add in the middle are not for free. It takes time to actually latch the data. It takes time to actually read the data from the latch. And there's some communication delay over here. So a more realistic pipeline, you actually don't get this beautiful behavior. Basically, this is the non-pipeline version. You really always have a latch delay. Your throughput is really 1 divided by t plus s, where t is the combinational logic delay, s is the latch delay. As you pipeline this deeper and deeper, what you get is with a k-stage pipeline, your throughput is 1 divided by t divided by k. You can divide the delay of the entire operation, if you will, by k, assuming you can partition the steps equally. But you get the latch overhead, right? You always have the additional latch overhead. That's plus s. So in the end, the minimum you can have this particular pipeline stage is 1 gate delay, right? And your maximum throughput is really this one. You're really limited by 1 divided by 1 gate delay plus s over here, which is a latching delay. So people have actually looked for what is the ideal pipelining level in processors. This is way worse than the ideal, because this is actually adding a lot of overhead into the system. Because you really need to be able to partition your instruction processing into 1 gate delay chunks, right? So at every pipeline stage, you have only 1 gate. And then you latch. And then you go to the next gate, and then you latch. Well, that's very hard to do, actually. What do you guys think? How many gate delays are in a pipeline stage in modern processors? Anybody has an idea of that? Ballpark. I'm looking for ballpark. 10 to 15 is a good ballpark, actually. You're right. 10 to 15, 10 to 20, something like that. People try to push it down to like 6 to 8, actually, or even 4. But it turns out you get a lot of overhead, because now it's very hard to uniformly partition the operations, for example. That's one overhead. There's also overhead in terms of clocking, which you will not get into. But 10 to 15 gate delays is what a lot of modern processors have, or 10 to 20, if you want to include all of the processors. OK, so latch delay reduces throughput. It leaves a switching overhead between stages. It also increases cost, right? If you look at cost, the non-pipeline version, this is the cost is really some number of gates over here plus the latch cost. And here, with the k stages, what you really have is you're really dividing, assuming you can do this ideally, you're really dividing g by k. In most cases, you cannot do this ideally, because you cannot uniformly partition the gates. And basically, you're keeping the number of gates constant. Even with that optimistic assumption, as you add pipeline stages, you're really multiplying the latch cost with the number of stages. So it becomes expensive, actually, once you make your pipeline deeper and deeper. I think the deepest pipeline that I know of was Prescott, Intel Prescott, that had 29 stages or so. Or maybe 30 stages. It may be 30 stages. I'm not sure. You can read the paper related to Prescott. And then after that pipeline, Intel went back to the core microarchitecture, which has much fewer pipeline stages. like 12 to 15, I believe. But that was at the time when they wanted to push the clock frequency higher. So the benefit of this is you can push the clock frequency higher also, right? Because you have fewer gate delays. Your combinational logic delay is much smaller. But we will see the downsides also. Well, one downside is cost. The other downside is actually energy, right? Because you're really adding all of these new latches, and you're clocking everything at the same time. As a result, you're really consuming a lot of energy. If you're increasing frequency, you're consuming energy on top of that also, if you remember the CV square F equation with power, right? OK, so it's good to think about what is the optimal number of pipeline stages. I don't expect you, that won't be a question on the exam. That involves a lot of other things that you will not learn in this course. It's always good to think about. So latches increase hardware cost. And even, I will mention this. This is still an ideal pipeline, actually, because it's very hard to uniformly partition these, as we will see later. It's very hard to balance the pipeline stages, if you will. Very hard to balance that. OK, let's talk about instruction processing. Basically, we would like to pipeline this instruction processing cycle, right? And I'll go back to what we've used earlier: fetch, decode, register file access, execute/address generation, memory, and write back. This is a single cycle microarchitecture that we covered before. And this is the bandwidth that we've just discussed, right? It's 1 over t, where t is the combinational logic delay that you have in the single cycle. Let's try to divide into stages. And this is one division into stages that I'll just give you. This is instruction fetch. It takes 200 picoseconds. This is instruction decode and register file read in parallel. It takes 100 picoseconds. Execute address calculation, 200 picoseconds. Memory access, 200 picoseconds. And write back, 100 picoseconds. This is a reasonable division, right? But even with this division, you see that it's imbalanced, right? Not everything is 200 picoseconds, or not everything is 100 picosecond. So what do you do to balance it? Maybe you can try to divide this into 2 stages, right? Such that each stage takes 100 picosecond. Right? But that may be a difficult thing to do, especially with the memory structures that you have over here. You can try to pipeline your ALU and adders over here such that each stage over here takes 100 picoseconds. Right? That's actually a technique that's used in many, many systems. Intel Pentium 4 had a pipeline, very, very aggressively pipelined ALU, 3-stage pipelined. Adder, this is just an adder, basically. Multipliers are almost always pipelined. And then you can divide this stage also. But those actually add cost. So we're going to assume that this is the pipeline that we have. And you need to somehow write to the register file. That's what this arrow is about. And start thinking about what you need to do with this signal over here. Well, this signal is a branch target address, right? If you remember. Basically, if you have a branch that needs to take the target, what do you need to do with the instructions that are here? Have you already fetched those instructions after the branch? Well, what did you assume when you were fetching those instructions? You assumed we went to the next sequential instruction? These are some of the issues that control flow instructions cause in a pipeline. Right? OK. Is this the correct partitioning? Well, that's always a good question. Who knows? Depends on your design point, again, here. But it's one partitioning. It may not be the best partitioning because you have imbalance in the stages. Why not have 4 or 6 stages? Or why not have different boundaries? These are all good questions. I mean, this is, when you're designing a pipeline, you need to think about how to balance the stages. And there's no perfect way of doing it, really. Let's look at the throughput of this pipeline. This is the, I guess I should really be using this, huh? That way everybody can see what I'm pointing to. Maybe I'll stay away from this machine. OK. So this is a load over here. This is another load, another load. These are independent loads, as we've seen before. This entire load in a single cycle machine takes 800 picoseconds. In a single cycle machine, assume that the delays are as low as possible, right? In a pipeline machine, if you look at this, each load goes through 5 stages, and each stage is 200 nanoseconds. Is this correct? OK. Well, something is happening. Yes, 200 nanoseconds, even though I don't show you here. Each load ends after 1,000 nanoseconds. Right? We've actually increased the delay of a single load, right, by pipelining. I'm not even counting the latches over here. Even without counting the latches, the delay of the load is now 1,000 nanoseconds. Why? Well, because we have this idle stuff within pipeline stages, right? In a single cycle machine, each portion of instruction processing took as long as it took. But here, you partition the stages, and every stage is controlled by the same clock. As a result, you have to obey the same latency, right? Register file access, even though it takes only 100 nanoseconds, well, too bad. You wait 200 nanoseconds to latch the results. As a result, you increase the latency. So that's one downside of pipelining, as you can see. Not only cost, but also increased latency, because every instruction goes through this pipeline. And as a result, what you get over here is basically 3 loads. You complete them. Well, you complete 1 load every 1,000 nanoseconds, right? Is that true? No, every 200 nanoseconds, sorry. 1 load every 200 nanoseconds. Whereas over there, you were completing 1 load every 200 picoseconds. I guess to map the nanoseconds to picoseconds. You complete 1 load every 200 picoseconds, whereas on top, you were completing 1 load every 800 picoseconds. So your speed up is really 4, even though we had 5 pipeline stages. So it's not a perfect pipeline, as you can see, right? Because we couldn't partition the operations really well. If you had divided these to 100 nanosecond pipeline stages, then you could get the ideal model. The problem is now we didn't include the latch overhead in this calculation, right? You'd actually go through, if you divide it into, let's see, instruction fetch takes 2 stages, 2, 1, 2, 2, 1. That's 8-stage pipeline. If you have an 8-stage pipeline, you can have 100 nanosecond latency for your pipeline stage. As a result, you can improve throughput by 8, right? But you remember to count the latch overhead also, latch delay. OK, so what do you need to enable this? Remember, we're trying to divide this entire combinational logic delay into, in this case, 5 stages. So we need to add pipeline registers, basically. And that's what the pipeline registers look like. Basically, you need to, after the fetch, you need to store the results in a temporary register, which is a pipeline register. And that way, you can actually do the decode for that instruction in the next stage, or access the register file also at the same time for that instruction in the next stage, while you're fetching some other instruction over here. Pipeline registers enable that. Basically, they partition the pipeline into different resources that can be operated independently. Make sense? So this is additional cost. What needs to go into the pipeline register? It could be actually a lot of overhead. Well, these are some things that need to go into the pipeline register, right? For example, you need to have the PC plus 4, and at the end of the instruction memory access, you have instruction register over here. And at the end of decode plus register file access, you still need PC plus 4, because you need it for branch target calculation later. And you have operand A and operand B and an immediate that was formed over here. Now your pipeline register is growing, right? Maybe. And at the end of this stage, you have this next PC, which is a target address, potentially, and some result of the ALU and some other thing that you pass that you may need later on. Right? So whatever you need later on, you need to pass down into the pipeline registers, and you need to store them in the pipeline registers. So the key is to ensure that no resource is used by more than one stage. And let's take a look at the operation, and then we'll go back to what happens to the control over here. Right now, we're just looking at the data path. So all instructions must follow the same path and timing through the different pipeline stages. That's the beauty of the regularity of the pipeline. That also causes the overhead. So if you look at this, fetch, decode, execute of the load, memory, access memory. And if you look at this, the load is not exercising everything, right? If you look at it, for example, here, the load is not exercising the branch pipeline, or the branch target address calculation engine over here. Right? Load is not a good example because load actually goes through all of the stages, right? OK. So there is a performance impact to this, right? Once you, because all instruction class must follow the same path and timing, you get some performance impact. An instruction, it may not need memory. It may not need one stage, if you will, but it still needs to go through that stage. For example, an add instruction. There's no reason an add really needs to access memory, right? But it still needs to go through that stage. Otherwise, you'll have a very irregular thing in the pipeline. Does that make sense? So an add still takes 1,000 nanoseconds, even though it doesn't need to take 1,000 nanoseconds. It doesn't. You can skip the step for the add, right? Make sense? Okay. So that leads to the performance impact. So let's look at load and subtract over here. If you look at this, you can basically pipeline the operation of these. But we'll see that life is not always this beautiful. So if you look at this, the reason you can do this pipelining between this load and subtract is because subtract is not dependent on the load. Right. So the load's destination register is register 10. Subtract doesn't source from that destination register. So you'll somehow need to detect that, first of all, to be able to do this, right? If subtract was dependent on the load, so I'm foreshadowing what we will see later, you shouldn't do this, right? Because by the time subtract gets to the ALU stage over here, load has not even accessed memory yet. And if subtract was dependent on the load, you cannot do this, basically. Subtract cannot move on because load has not even written the register file yet with its result. Where subtract is supposed to get that register value. Does this make sense? Okay. I'm not going too fast, right? Stop me if I'm going too fast. Because this is important to realize. Okay, I'll go through these relatively quickly just to look at the concept of steady state again. So if you look at the operation view of a pipeline, this is time 0, cycle 1, ... cycle 5. In the first cycle, you fetch instruction 0. In the next cycle, you fetch instruction 1. Next cycle, instruction 2. Next cycle, instruction 3. Next cycle, instruction 4. And if we have a 5-stage pipeline, as we've discussed, in the 5th cycle over here, you basically have your pipeline full. This is called a full pipeline now. And in the steady state, you operate that way because you keep fetching instructions, and your pipeline is always full. So this is kind of your steady state, if you will. Ideally, you would like to sustain this. Always have a full pipeline. That way, you're completing 1 instruction per cycle. And this is another way of looking at the full pipeline. On the x-axis, on the rows, we have the stages. And on the columns, we have the time. And if you look at the stages at any given point, you have different instructions. Right? For example, when the pipeline is full, instruction 0 is in the write back stage, instruction 4 is being fetched. Now I guess you can visualize it as much as you like. It's kind of nice. OK, let's look at the control points in a pipeline. We've covered the data path, right? You divide the data path into multiple portions and isolated each of them from each other with pipeline registers. What about control? Well, control is very important. You have to control this thing. But if you look at control, not much really changes compared to the single cycle data path, right? You still have the same muxes. You still have the same memories. You still have the same registers. You just need to control them differently. Now the control is not for the instruction that's being executed at this point. Now different parts of the pipeline needs to be controlled separately, right? Because if you think about it, these are really separate parts of the pipeline. They're doing totally separate things. Even though control points are the same, you need to somehow do something different with the control signals. Basically, the control signals are the same as a single cycle implementation, but they're required at different cycles depending on the stage, right? Which means that what you can do is when you decode an instruction, you can decode the entire instruction and generate all the control signals using the same logic as you will do in your assignment in the single cycle implementation, as we've seen in 2 lectures ago, and buffer all of the control signals until they're consumed. In the end, your pipeline looks kind of like this if you do this. Basically, ignore fetch. You need to have a separate control for fetch because you don't even know the instruction at that point, right? After the fetch stage, in the decode stage, you decode the instruction. You go through this control logic, which could be hardwired or microprogrammed, microcoded. As a result, you get all the control signals that you need in this stage, in the memory stage, and in the write back stage. And you put them in a pipeline register. And after this, the control signals are consumed in each respective stage, you get rid of the control signals from the pipeline latch. So basically, you're propagating the control signals across the pipeline. Sounds like a reasonable idea, right? Basically, you carry only those control signals that you need. You need to do the same thing with the data, by the way. It's not I mean, you have to, for example, carry the program counter as long as you need. And then when we talk about the precise exceptions, you actually need to carry the program counter all the way to the write back stage, because your machine can be interrupted at any given time. But think about it. But this is not the only option again, right? You could actually, this is decode once and propagate. The other option is decode on demand, right? You could actually carry only the relevant instruction word or field that you may need later on and decode locally within each stage or in a previous stage. So if you, since you've been through my previous lecture, you will say that you have to decode in the previous stage, right? Because if you decode in the current stage, you're lengthening your clock cycle. Make sense? So in this case, you're really carrying only the instruction register, if you will, and maybe other things that you need to generate the control signals. So what you're carrying is relatively constant in the end. But you're generating the signals locally. This may actually reduce the cost of your pipeline latches. Well, I guess my next question was, which one's better? I gave you one reason why the second one might be better. It may reduce the cost of your latches, right? Because you don't carry all of the control signals that you need all the time. Because control signals are actually much larger than the instruction register, right? So which one's better? Any thoughts? Let me put it another way. What are the advantages of the second option? I said, well, I gave you one advantage. It could be smaller pipeline registers because these control signals may be a lot, right? What is the disadvantage? Yes?
Oh, I was going to say an advantage.
Yeah.
It would also more evenly distribute the decode logic than you would be putting on one stage.
That could be true, actually. That's a good point. That could be an advantage because maybe this control store is very complex, right? It may take a long time. Whereas if you do it locally, maybe it's not on your critical path anymore. That's a good point. What is the disadvantage? Is there one? There must be one, right? As I said.
Duplicating hardware probably.
That's right. You could be duplicating hardware, right? You could actually be generating the same or similar control signal again, right? You may be decoding the register ID several times for some reason, right? That's actually true. Any other disadvantage? OK, I'll let you think about it. It's actually simple. OK. But there's no best way, basically. You cannot, it's very difficult to get the best of both worlds. You have to do one or the other. If you come up with another one, let me know. Now you can have a combination of both. You generate some control signals and carry some of them, and you generate some of them locally also. In most systems, actually, you have that combination. OK, so these are the control signals for the pipelined implementation, which you will actually do in your lab. What is lab X? Lab 3, right? Yes. And you will actually improve the pipeline implementation in lab 4 and lab 5. In lab 4, you'll do branch prediction. In lab 5, you'll add the caches. So it'll be fun. You'll make it work. So learn this lecture really well. Because this will be the basis. Yeah, to foreshadow a little bit, you should really get the pipeline implementation right. Because that'll determine what will happen in lab 4 and lab 5. OK. So this is an example of the control signal. This is the write back signal that's propagated all the way until the write back stage. And it's only used at the write back stage. For example, this register write signal. You don't write to the register in this stage or in this stage. You really write to the register over here, right? So you only need that signal at this stage. You could have generated it later on, right? OK. Actually, this is a hard trade-off to make, because if it's just this signal, if you're generating only the write back signal, maybe it's OK to carry that, right? Because later on, if you carry the opcode or something like that, you need to have additional logic to decode that, well, maybe earlier. But that's carrying more stuff now, right? So it really depends on what kind of signals, how large your control signals are, how many control signals you have. So the answer is really, it really depends in this case. Does that make sense? Yeah. OK. OK, let's remember the ideal pipeline, and we'll look at how the instruction pipeline is not ideal. Remember, our goal is increased throughput with little increase in cost, and hopefully little increase in latency of an operation. Right? To be able to do this, we want identical operations. We want to repeat the same operation over a large number of inputs, like the laundry loads. Different laundry loads go through the same steps. We want to repeat independent operations, and we want to uniformly partition the sub-operations. Let's take a look at how instruction processing pipeline obeys these properties of the ideal pipeline. And it doesn't. It basically violates all of them, right? Identical operations, well, unfortunately, different instructions, as we've just discussed, do not all need the same stages, right? An add, for example, doesn't really need to go through the memory access stage, right? A branch doesn't really need to go through, I don't know which stage. You can pick memory access stage, for example, right? Unless you have a complicated branch instruction. Or write back stage, right? You could actually do the branching earlier, right? And we will see that. That's the idea of you don't need to wait until the write back. So forcing different instructions to go through the same pipeline stages leads to external fragmentation. What does this mean? Basically, some stages are idle for some instructions, but then you still need to go through that. This increases the latency of that instruction. Well, you give up some benefit. You give up something to get this higher throughput, basically. Uniform sub-operations. That's also not true, right? If you look at different pipeline stages, they're not the same latency, and I show you one example of that. Right? Some pipeline stages have longer combinational logic delay. Some pipeline stages have shorter combinational logic delay. It's very, very difficult to balance all of these stages. As a result, you need to force each stage to be controlled by the same clock. As a result, you get internal fragmentation. Within a clock cycle, within a stage, even though you're done early, well, you cannot proceed, right? You're just wasting the rest of the cycle because you have to take the same clock cycle time. Independent operations, that's also not true. Instructions are not independent of each other, at least in most programs. There is some independence, as we will see. Out-of-order execution will exploit that independence, actually. But there is a lot of dependence also. As a result, you need to detect and resolve these inter-instruction dependencies, right? Otherwise, your pipeline will be incorrect. Your pipeline will provide incorrect results if you assume that there is no dependency between instructions. As a result, you'll have pipeline stalls, which means that pipeline is not always moving. A pipeline stall means the pipeline needs to stop, and you cannot move the pipeline because you're waiting for something. And waiting for something could be the result of a previous instruction, right? Because the previous instruction has not reached the pipeline stage where it can produce that result yet. Make sense? So we'll actually concern ourselves a lot with this for the remaining few lectures. So that brings me to issues in pipeline design, all of these knots, if you will. Basically, first issue, you need to balance the work in pipeline stages. We're not going to talk about this a lot in this course, but a good architect has to balance the work in pipeline stage. And this is more at the lower level, how you design, how you divide your pipeline into multiple stages. And critical path design principle is very important, right? You've got to minimize the critical path while balancing the work. How many stages and what is done in each stage? The second thing that we will talk a lot about is you need to keep the pipeline correct, moving, and full in the presence of events that disrupt the pipeline flow. And there are actually many events. Life is not beautiful. It's always working against you. As an engineer, your challenge is to overcome all of those things that work against you, right? Dependencies. Well, data and control dependencies, we'll talk about these. Resource contention. One stage may need memory, another stage may also need memory. Now you have resource contention, right? You can duplicate the memory. Handling long latency operations. These actually disrupt the flow in the pipeline. What if an instruction takes 100 clock cycles, let's say? Well, do you make your pipeline 100 stages deep? Bad idea, perhaps, right? What do you do in that case? Well, we'll talk about that. Handling exceptional conditions and interrupts that are coming into the processor. Well, that disrupts the flow of the pipeline, right? If an instruction causes exception, how do you handle it? And we'll talk about improving pipeline throughput, minimizing stalls. So we'll cover a lot of these in the next 4 or 5 lectures, actually. Let's talk about pipeline stalls. What are the causes of pipeline stalls? And then we'll take a break. Remember, stall is a condition when the pipeline stops moving. And this is caused by three different things. It could be resource contention. It could be dependencies between instructions, data, and control. And control dependence is actually a form of data dependence, as we will see. And long latency multi-cycle operations. All right. I promised a break, so I should actually abide by that. Let's be back at 0010 India time. Hopefully you're not sleeping because it's 0010. Let's get started. Yes, we were talking about dependencies. Basically, these are things that can cause pipeline stalls. So let's take a look at dependencies and their types. This is also called dependency, if you will, or dependencies. Dependence and dependency is the same. Some books call it a hazard. I don't like the term hazard, because hazard sounds bad. Dependencies always happen. It has to be a part of program, right? If you want to be able to use the result of an instruction, you have to have another instruction that's dependent on that. There's nothing hazardous about this, right? A hazard happens if you don't handle that dependence correctly. Make sense? So if you see hazard in some of the books, rename it to dependence. And dependencies, I mean, they're there for a reason, right? These dictate ordering requirements between instructions. Right? There are two types of it, data dependence and control dependence. And control dependence, as I said, is a special form of data dependence, really. Resource contention is sometimes called resource dependence also. You're dependent on a resource in that case. But it's really not as fundamental, right? Because it's really not dictated by the program semantics. So we will treat it separately. As we will see, actually, some forms of data dependence are actually not fundamental also. They're really dictated by the architecture constraints that you have. And we will see that soon. So resource contention, let's talk about that first and get it out of the way. It's important. This happens when two instructions in different pipeline stages need the same resource, right? For example, it could be register file, right? You have one port in the register file, one instruction needs to write to it, and the other instruction needs to read from it. Now you have resource dependence on the register file. Well, how do you fix the problem? First, one solution direction is to eliminate the source of the contention, right? You can duplicate the resource. And we will actually have a lecture talking about how to provide high bandwidth memories later on. Basically, how do you duplicate the resource? You can add more ports into the register file. That's one way. You can duplicate the register file. That's another way. Or you can increase its throughput. That's another way, actually. Or you can come up with more clever techniques. You can time multiplex a port. We will see that as actually. It's called virtual multiporting. You really, at the beginning of the cycle, you write to it. In the remaining part of the cycle, you read from it. And you can get the value that's written. That's one way. So there are different ways of eliminating the cause of contention, basically. I guess in terms of the caches, you can separate instruction and data caches, right? And we've already talked about the multiple ports. The second solution is, well, this obviously has a disadvantage that you're really increasing the cost, right? All of these solutions increase the area somehow, or increase the complexity. If you're doing time multiplexing, that increases the complexity. The second solution doesn't increase the area as much. You can detect the resource contention and stall one of the contending stages, right? You can say, I want to first write to the register file, so read. You can wait for a while this write is finished. Then the question is, which state do you prioritize, right? Because this could lead to issues if you prioritize the wrong one. Or which state do you stall? For example, what if you had a single read and write port for the register file? Which one do you stall? Do you stall the instruction that's reading the register file, or do you stall the instruction that's writing into the register file? Remember the pipeline? Picture the pipeline in your head. Reading. You stall the one that's reading because the writing instruction that's writing to the register file is really blocking your pipeline, right? Your pipeline is not moving. That's at the end of your pipeline. And even if you prioritize this instruction that's reading, well, where do you put it, right? Because the pipeline hasn't moved. Okay. Well, this issue becomes even more interesting when you have multiple functional units in an out-of-order machine, for example. We'll talk about that when we get to it. Okay, so these are the two fundamental ways of handling resource contention. Keep this in mind still. But let's talk about even more fundamental reasons of contention or stalls. And those are data dependencies. There are three types of data dependencies in a program. flow, output, and anti-dependence. The only true ones are really flow dependencies. This is basically an instruction is reading a value that's produced by another instruction that wrote that value, register, or memory. We'll talk about values for now, because what you're doing is really value communication. It could be communicated through the registers or through memory. There are two other ones, output dependence and anti-dependence. An instruction is writing a register that a previous instruction wrote to. An anti-dependence is an instruction is writing a register that a previous instruction read from. And these could actually cause issues in a pipeline. Well, all of them actually can cause stalls in a pipeline machine. Can you guys think about why? Well, we'll see. For all of them, we need to ensure semantics of the program is correct. Right? What really matters is that, remember the von Neumann model? Von Neumann model says you process one instruction at a given time and you move to the next sequential instruction only after this instruction is done. Well, pipelining violates that, right? A microprogrammed machine, multi-cycle machine, didn't violate that. You still finish the instruction to move on to the next instruction. Whereas pipelining, you actually violate that. That's why this becomes an issue in pipelining. Because now you're really moving to the next instruction before the previous instruction is finished. So if you don't update your state correctly, if you don't detect these dependencies, then you may get wrong results from the sequential instruction point, sequential instruction processing viewpoint. So flow dependencies always need to be obeyed because they constitute true dependence on a value, right? Basically, one instruction is really dependent on waiting for the value that's produced. Those are really the fundamental dependencies. Anti and output dependencies exist due to limited number of architectural registers. These are not as fundamental, actually. And we will see that. They're dependent on a name, not a value. So if you're writing, if an instruction, if you have a multiply that's writing to register 5, and you have an add that's writing to register 5, and there may be some stuff in between, the register 5 has nothing in common between them, right? They're really, register 5 is just storage in that case. They're not really communicating those values, assuming these instructions are not dependent through some other way. Register 5 is just a storage where these instructions store their results. If you had infinite registers, there's no reason to have those instructions write to register 5, right? Because they're really producing different values. So these anti and output dependencies exist due to limited number of registers. They really depends on the name and not value. And we'll later see what we can do about them, actually. We could actually eliminate them by renaming. So you can, I'll do a flash forward. Instead of having two instructions in the machine writing to register 5, you rename register 5 into two different things and provide different storage internally. That way, now you've eliminated that dependence, right? Because now they're writing to different places. Does that make sense? Not yet? OK, it'll be clear later on. That's called renaming. So if you, let's take a look at this. This is a flow dependence. The first instruction is producing register 3. The second instruction is consuming register 3. So this is fundamental. You cannot get rid of this dependence, right? You have to produce it to consume it. That's the read after write dependence. Now, this is what I mean by not fundamental. This is anti-dependence. The first instruction is using R1, reading, to produce some value. The second instruction is redefining what's in R1, writing some totally independent thing into R1. It's called write after read. But if you look at it, there's really no dependence in these instructions in the program communication sense, right? There's no value communication that's going on. It's really a name dependence. If you had R1 million, you could have just said R1 million here. You couldn't do that over here. R3, it has to be R3. That's the semantics of the program, right? Whereas here, you could do, if you had enough registers, there's no reason to reuse R1. Same as output dependence over here. So if this instruction is writing to R3, this instruction is also writing to R3. And ignore this. This basically ensures that this R3 is not dead. Someone reads, actually, that instruction. Basically, both of the instructions are writing to R3. Again, this is not a fundamental dependence. If you had R1 million, you could just say this is R1 million, right? But these are real issues because you don't have an infinite number of registers in the ISA. So some instructions write to the same register, even though there is no relationship from the program semantic point of view between those storage locations. OK. But these cause issues in a pipeline machine. But we'll see that you can actually eliminate these by renaming, by providing additional storage and pointing this R3 to some other location than this R3 points to. Make sense? The problem is you don't have enough names here. Okay, so let's take a look at the pipeline operation. I'll go through this quickly because we've seen it. It's nice if subtract is not dependent on load over here. But if subtract was dependent on load, what needs to happen is you need to stall the subtract somehow, right? Then the question is, where do you stall it? So here, load is writing to R10. Assume that subtract is writing to R10. At this point, load reads its registers. It goes into the next step. Subtract now needs to read its source registers. Sorry, this shouldn't be R10. This is the destination register. Assume that this R3 is R10. Subtract needs to source R10 over here. But R10 is not produced yet. R10 will be produced only after load writes it back into the register file. So at this point, you need to stop subtract, because subtract cannot go because it doesn't have the value. Because R10 is really not ready. It's not really produced at that point, right? So you should let the load go, finish it, and once the load is done, now you can move the subtract, right? So you need to somehow inject empty cycles or bubbles into the pipeline such that load can continue, subtract should stay, and everything else should stay, should not move, until the load actually produces the result, and subtract can read it from the register file. Make sense? So we'll need to do that in a pipeline machine. Okay. So to be able to do that, we need to handle the data dependencies. Okay, I'll give you some readings for the next few lectures. This will actually cover, this is a 25-page paper. It's actually a very good introduction to a lot of things that we will talk about. More advanced pipelining, interrupt and exception handling, and out-of-order and superscalar execution. So hopefully you'll start reading it. Actually, we have a couple of other things over here, but I'll give that later. So basically, how do we handle these data dependencies? As I said, anti and output dependencies are easier to handle. In a pipeline machine, at least, what you can do is you can write to the destination in one stage and in program order. That handles your anti and output dependencies, right? Make sense? Well, you need to do maybe a little bit more other things. You got to be still careful. Assuming that you still stop the pipeline, you can handle a lot of the output and anti-dependencies this way. But we'll get to this. Flow dependencies are actually more interesting. And there are 5 ways of handling flow dependencies, in my opinion. 5 fundamental ways. If you come up with another one, let me know. Well, the first one, detect the dependence and wait until the value is available in the register file. That's what I described earlier, right? Subtract waits in the register file stage until the value of the load is produced. Simple, clean. And we'll see methods of doing this. But it's not that aggressive, right? You can be a little bit smarter about this, because load value is actually produced before it's written into the register file. Right? So you can detect the dependence and forward or bypass the data to the dependent instruction when the value is available. Right? So load accesses memory at the memory stage. You can take that value and bypass it or forward it to the subtract. That way you don't need to wait until the end of the write back stage to move subtract. That's one way. Any other ideas? Here's where you can be creative. I gave you only 2. We'll cover some more. Yes?
Is it possible to insert some other instruction in between the pipelines so that you don't have to wait, you can just execute something else?
That sounds great. Which instruction?
You have to pick some independent.
Independent instruction. That's right, you could do that. Not with the simple pipeline, though. With out-of-order execution, that will be the idea, yes. And that's a great idea. Basically, execute something else, what you're saying, right? Not the dependent one. There's actually a really simple way of doing it. Well, really simple. You don't need to find those independent instructions. What if you already had those independent instructions? Compiler can give it to you. That's right, yes. Let's see. That's what you can detect and eliminate the dependence at the software level, right? Basically, somehow the software, actually, it doesn't have to be an independent instruction. It could be a no-op also. The software says, okay, I have this load and subtract. Instead of putting them right after each other, I'm going to find some independent instruction, and an instruction that's independent of the load, and insert it right after the load. This way, the pipeline can keep moving, right? And if I cannot find an independent instruction, too bad. I'm going to put a no-op in there. This way, you don't need to detect the dependence, right? The hardware doesn't need to detect the dependence. That's the beauty of the software solution. You do basically instruction scheduling, static instruction scheduling, such that instructions are scheduled to maximize the utilization of the pipeline. You always get one instruction per cycle, hopefully. And you don't need interlocks in the hardware. Well, interlocking, I didn't say that, but interlocking is the hardware that's needed to detect the dependence. You don't need to detect that dependence even. Make sense? We'll actually cover this in a later lecture when we talk about static instruction scheduling, but this is a very valid solution. In fact, this was a solution the designers of a lot of RISC architectures, remember RISC from a few lectures ago? MIPS, for example, pursued. What they said was pipeline will be very simple, no interlocking, no hardware dependence detection. In fact, remember the MIPS acronym? Microprocessor without interlocking pipeline stages. Well, everything. Compiler handles all of the detection of dependence of instructions and schedules instructions appropriately such that you don't need to do any dependence detection in hardware. When the compiler can find independent instructions, it's a great idea. When the compiler cannot, what you end up with is a lot of no-ops. If your load takes 5 cycles, and if you cannot actually have enough independent instructions to cover that latency, you have a lot of no-ops. And we will see that also, actually. OK, that's 3. What else? Actually, your solution covers a lot of other solutions. This is one specific version of that. The other one's out-of-order execution, actually. 2 more. Maybe I should really expand this, because I don't know if I have out-of-order execution exactly here. But I wasn't thinking about a more complicated pipeline. I was thinking about the simple pipeline with some potential additions. What else can you do? Where else can you get the independent instructions from, assuming that you don't want this additional logic to figure out what's independent and dependent? Software does it nicely because it does it offline, right? Can you get independent instructions from somewhere else? Yes?
If you're running like 2 threads.
That's right. 2 different programs maybe, right? Well, too bad. I have an out-of-ordering problem. But yes, that's the 5th solution over here. All right, I'll give it to you. That's too bad. Because this is kind of a cute solution too. But do something else. Basically, you don't need to detect. You just switch to something else. And we'll see a solution called fine-grained multithreading in the next lecture. Whoa. OK, India is, I guess, 30 minutes different. So I thought we were already over, but we're not over. Basically, you switch to some other thread. In one cycle, you fetch from thread 1. In the next cycle, you fetch from thread 2. In the next cycle, you fetch from thread 3. In the next cycle, you fetch from thread 4. In the next cycle, you fetch from thread 5. Now you have no need to detect any dependence because you know, assuming that all of those threads are independent, there's no dependence to begin with. And your pipeline is full from instructions with instructions from different threads. That's called the idea of fine-grained multithreading. As long as you have 5 threads to fetch from, as long as you can keep your pipeline full, it's a beautiful idea, right? You don't improve the throughput of a single thread. In fact, you degrade it compared to fetching instructions from that thread always. But you improve the aggregate throughput of the entire system if you have something like this. Modern GPUs operate this way. They actually heavily employ fine-grained multithreading across different warps, if you will. And we'll see what a warp is, across different threads, basically. Because they have so many threads. If you think about rendering a screen image, right? There are lots of pixels. And it can generate many, many threads that can operate on different portions of the image. And modern GPUs, in their pipelines, they don't have dependence detection logic. Because you have enough parallelism, enough threads, and every cycle you fetch from a different thread. It's a beautiful idea. So this idea is already employed, actually, in existing systems. Actually, it's employed in other multi-core architectures also. Well, the last one is actually the 4th one over here, which is kind of nice also. If you don't have the value yet, well, why not predict it? I don't know register 5. It's not available yet because there's a load that's going on. I'm going to assume that it's 0. I'm going to execute this add, assuming that that value of register 5 is 0. Good idea? Depends. If the value is really 0, it's a good idea, right? Which means that you've got to verify the value. If the value is really 0, then, and assuming you verified it, that's good. You're done. You didn't need to incur any delay. But if the value is not 0, if it's incorrect, you need to check, first of all. You need to add some other logic to check whether your prediction is correct. And if it's incorrect, then you need to do something special, which means that you've executed it wrongly, right? So you need to back up and re-execute. This is called the idea of value prediction, predicting the value. And it can break that dependence. Basically, what you're doing is really breaking that dependence. And assuming that you're really confident that that value is going to be 0, why not? No, sounds bad. You guys are not convinced. How do you do this? Can you imagine? This could be a good exam question, by the way. How would you implement a value predictor? Well, one thing, I'll give you one idea. You basically track in hardware the instructions that are executed. You have a table. All right, this kind of prepares you for the branch prediction lecture. So start stretching your mind. I guess I need a pen. All right. Can you see it? OK. Let's say you have loads R10. This has a program counter X, right? And then you have loads at program counter Y. It's loading R15. And I don't care where it's loading from. The first time you execute the load, you execute it regularly somehow. And record the result that you get. So the first execution, let's say R10, gets the result 0. Basically loads the value 0. And let's say we add a hardware table into the machine. And what this table does is, I'm going to be abstract here. For a given program counter, it stores the last value that's seen. Right? You can have 0, 1, ... It can be content associative memory. You guys know content associative memories? Content addressable memories? All right, no, let's ignore that for now. Let's assume that we have a table as input. I can give it a program counter. We'll see content addressable memories, by the way, when we talk about out-of-order execution. I don't want to introduce it right now. But I can give it a program counter, and I can get the last value that was stored, that was loaded by that program counter, that was produced by that program counter, the last time it was executed. Make sense? The first time I execute this load, I get a value 0 from memory. I place that last value 0 into this table, such that I can later look it up. The first time I execute this load, I associate PCY with the last value that was loaded. Let's say the loaded value was 1,000. OK? And the next time, let's say, we execute this load, because the program consists of a loop. At some point, you go back to this load, right? Maybe you execute with a different address, but the next time you execute, you say, oh, I'm going to predict that it's going to have the same value as the last time. Right? That's one way you can remember. You record the last value that you loaded with that load, and the next time you execute that load, you use that last value as a prediction. Does that make sense? And if it's correct, that's great. You can say, oh, maybe you add another bit over here saying, oh, I'm really confident that I always start getting zeros with this load. It's called the confidence bit, if you will. The last n times I execute this load, I saw zeros. So I'm going to predict the next time I execute this load, I'm going to get another 0 from memory. Make sense? It may make sense, right? What if you're going through a sparse array? A lot of the elements are all zeros, but there are some elements in the middle that are 1, 2, 3. Well, then this value prediction makes a lot of sense, right? Because almost always you're loading zeros. almost always you'll be correct. And you don't need to wait until that load actually finishes to do the operations that come after it. Only sometimes you'll be wrong. Except when you're wrong, you got to correct yourself, right? Somehow you need to ensure that you execute the program correctly. Does that make sense? Yes.
We have to make sure that this also doesn't fall into the critical path because we are putting in a memory and which is content accessible.
Absolutely, yes. Absolutely. So you're thinking, well, you need to ensure that this doesn't increase your critical path because actually it may be okay to increase your critical path a little bit if you're gaining a lot from not stalling, right? And that's actually the trade-off between frequency and IPC. That's actually a very interesting trade-off, right? Or CPI, if you will. Basically, doing this may reduce your CPI because you're reducing your stalls, right? It may increase your frequency slightly. It may reduce your frequency slightly. If the increase in CPI is much greater than the reduction in frequency, that may be a good option, right? Ideally, you don't want to reduce your frequency. Sure, I agree with that. But it's always, CPI and frequency has a trade-off between them. And that's good to know. Almost always, whenever you reduce CPI, or whenever you increase frequency, you reduce CPI. Because you're either pipelining deeply or doing something, unless your design is inefficient to begin with. Make sense? So I've given you the idea of value prediction and a simple implementation of a last value predictor. So this could be the last value predictor. Basically predict the value that was loaded by this instruction at the same program counter as the value that's going to be loaded right now. It may make sense under some conditions. Not in most conditions. If you're going through an array that has all random values, good luck, right? You'll always be wrong. Yes?
Is the prediction really worth it if you find out you predicted wrong and then need to go back
Yes.
and like do a lot of fixing?
Yeah.
Or-
So exactly, then that's the question, right? Now you're going into the question of how often do I need to do fixing? And how long does it take to do the fixing? Because that all affects your cycles per instruction now, because you're adding extra cycles. You're right. So if the savings you get from doing this prediction does not outweigh the cost of fixing it, then it's a bad idea. So whenever this is used, you normally use it with this confidence. That's why I added that confidence over here. If you're really confident, this may be a good idea. Now, a lot of modern processors don't implement this yet, but they may. We'll see a lot of similar things in branch prediction. But now you can develop some intuition as to why this may work, right? Because your data values may be very predictable. Okay, let's move on. Now you've seen 5 fundamental ways of handling dependence, and we're going to walk through some of these. I've already discussed interlocking. Well, interlocking is the detection of dependence between instructions in a pipeline processor to guarantee correct execution. And there are 2 ways of doing it, software-based versus hardware-based. Software-based we already talked about, right? Basically, software figures out the dependencies, knows the structure of the pipeline, and inserts independent instructions such that you never stall. That's the idea of MIPS, right? Microprocessor without interlocking pipeline stages. That's the flash forward a little bit. Well, actually, let's go backward a little bit. Load delay slot. You remember the load delay slot? Well, that's the reason for the load delay slot. The next instruction that comes after the load is always assumed to be independent, right, in MIPS. Why? Because they didn't want to add logic to detect that dependence on the load. Now what they can do is the compiler ensures that the instruction that comes after the load is always independent, or it's a no-op, and the hardware doesn't need to do any stalling for that particular case. That's why they had the load delay slot. Make sense? Yes?
Why did they assume that load completes in 1 second?
That's right, yeah. That's the downside of the approach. That's always the downside of this delay slot-like approaches. What happens if the load takes 10 cycles? It doesn't work, right? If you have a single delay slot, too bad. So the mistake over there was they designed the architecture assuming a particular pipeline where the load takes 1 cycle. In 10 generations later, when the load takes 5 cycles, the compiler still needs to ensure this property, load delay slot, but it doesn't help much, right? But you still need to detect that dependence in hardware, assuming you don't want to insert all no-ops over there. So that's the downside of the delay slot approach. We'll see that with the branch delay slot also, actually, in the next few lectures. But basically, the implementation details of the microarchitecture is kind of tied into the ISA. The ISA has, oh, I have a load delay slot. The reasoning was to actually not to do this interlocking in hardware. Okay? So the alternative is hardware-based interlocking, which we will cover right now. So hardware-based interlocking requires dependence detection in hardware. There are 2 approaches to it. One is scoreboarding, at least in a simple pipeline. Scoreboarding means basically you have each register in the register file has a valid bit associated with it. Maybe I'll draw it, maybe not. And each instruction that's writing to the register resets that valid bit when it goes to the, where's my pipeline? Oh, there's my pipeline. So when you actually, you determine whether you're writing to the register file over here, and basically we augment the register file. Maybe I should use a different color, as long as I have a different color. There you go. I have 3 different colors. Oh, that's maybe 2 different colors. So basically, for each register, we have a valid bit. Register 0, register 31, ... This valid bit says, is the data value in the register file valid? Meaning that no instruction later is going to store something to that. And if it's not valid, if an instruction is writing to that register later, because write back happens in this write back stage, right? If you decode an instruction that's writing to register 0, let's say, you set that valid bit to 0. Now the instruction keeps moving. A later instruction sources register 0, it checks the valid bit. Valid bit is 0, that means that that value is not available yet. I'm going to stall. That's how you generate your stall signal, right? It's simple. And it needs to check all of its source and destination registers. It needs to check its destination registers also to ensure that there's no write after write dependence, right? And if any of them is not valid, then you stall the instruction. If all of them are valid, there's no need to stall. There's no instruction in the later pipeline stages that is going to interfere with this instruction in any way. Make sense? That's the scoreboard approach. And when the instruction that's writing to register 0 comes to this stage, let's say, I don't know, it's an add, it basically writes its result and at the same time sets the valid bit so that the next instruction, the instruction that's waiting over there, can move. Make sense? It's simple. Well, I already told you. Simple. 1 bit per register. That's it. Yes?
So what problem would write after write cause?
We'll get to it.
Okay.
That's the next thing I'm going to ask, actually. Disadvantage. Because of the design of what I've described, you need to stall for all types of dependencies now. Why? Because let's assume that, now this may be a case that's not very common, but let's assume that an instruction is writing register 3, and immediately after that you have another instruction that's writing to register 3. You may ask why that's happening, but it may happen, right? This add sets the valid bit to 0, right? And it moves. Now this add comes in. Well, let's do this a multiply so that they're not both adds, so that we can distinguish between them. This multiply, let's assume that everything else is independent. Okay? This is writing to register 3. This is also writing to register 3. You need to ensure that the writes happen in the correct order, right? If you just have the valid bit, if you don't stall this instruction over here, then what will happen is this instruction will write to register 3 before, well, you have a problem of which one writes to register 3, right? You don't know which one will update the register 3. Does that make sense? Actually, in this design, I guess it'll work correctly. Yeah, in this design, it'll work correctly. You're right. Because what will happen is this, at least with this code, you have add R3 that will write to register 3. Oh, wait, let me think. Yes, so the problem is this. I need one more instruction. Even though this is kind of a stupid code, that's OK. Let's say you have another multiply or load that's sourcing R3. Can you guys see this? OK. So yeah, now I found the problem here. So you have add R3. You have when it's is writing to R3. Let's assume that you didn't reset the valid bit. You kept it as 1. Or you reset the valid bit because other instructions that are dependent on it should stop. Now this multiply is also writing to R3. Let's assume you let it go. If you let it go, what will happen is at some point this add will write to R3, right? And this load will be in this stage, right? And this add, when it writes to R3, it will set the valid bit. Make sense? So this load will get the incorrect value. Yes. So that's the problem. Of course, you wouldn't design something like this. So how would you fix the problem? Well, one potential solution is to actually have a counter instead of just a single valid bit. Right? Instead of having a valid bit per register, you have a counter that gets incremented whenever you have an instruction that writes to that register. It basically says how many instructions are there in the remaining parts of the pipeline that are writing to this register. And when an instruction writes to the register, you decrement the counter at the write back stage. And when an instruction is trying to read from that register, you basically stall that instruction if the counter is not 0. Make sense? So that way you can handle the correct behavior in the write after write dependence or write after read dependence. Or another solution actually is tagging. You can tag which instruction is actually writing to that particular register. And when you actually, when an instruction is trying to write to a register, you compare the tags. But we'll get back to that. OK, is this clear so far? OK. So there's another approach to dependence check logic, which is which doesn't look like a scoreboard. Actually, you don't really need the scoreboard. You can actually do everything combinationally, right? If you look at the scoreboard, it's really sequential. You add the storage. Whereas you could do everything combinationally. You can have special logic that checks if any instruction in later stages is supposed to write to any source register of the instruction that's being decoded. Now, that's a mouthful, but it's pretty simple, right? Basically, I should have another copy of this. You have the IDs of the source registers, source 1 ID and source 2 ID. And let's assume you keep the pipeline moving somehow. And you have some ID for the destination register for the instruction in this stage. And you have some ID for the destination register for the instruction in this stage. And you have some ID for the destination register for the instruction in this stage. Now, when you're trying to decide whether this instruction should move to this stage or not, what you need to do is compare the source ID 1 to all of these destination register IDs. And if any of them says, yes, they match, then you stop, right? And this the same is true for the source 2 ID. You have comparators. You compare the second source to any of the destination register IDs over here. If any of them match, another AND gate, you stop. Of course, you need to do the OR here to have a single stall signal, right? Does that make sense? That's the combinational dependence check logic. It's not enough, obviously, because you need to still handle the write after write dependencies, right, somehow. But I'll leave that to you when you design your machine. Make sense? So this certainly looks more complicated than the scoreboard. Scoreboard is very simple, right? But the advantage is you actually don't need to stall an anti and output dependence in this case if you handle them correctly. Right. What you need to do to handle them correctly is you need to ensure that the right instructions write to this register file. I guess in this case everything will move correctly because you're actually checking all of the dependencies, right? Actually, you don't really need to handle the write after write dependency as long as you do this logic correctly. Okay? The downside is the logic is more complex, obviously, than a scoreboard. And logic becomes actually more complex as we make the pipeline deeper. Think about a 20-stage pipeline, right? It becomes very difficult to compare all of those IDs. And it's a lot of wires to actually communicate. And what happens if you actually have multiple instructions in a single pipeline stage? If you have, let's say, a lot of the machines today actually can execute 4 instructions per cycle. You have 4 instructions in a pipeline stage. Now you need to check those dependencies also. So we'll see that when we get to superscalar execution. So once you detect the dependence in hardware, what do you do afterwards? I guess I'll cover this and then we'll part. Basically, the observation is you have a dependence between 2 instructions, and you can detect that before the communicated data value becomes available. Right? The value is not available yet. The first option is you can stall the dependent instruction right away. Right? That's what could happen over here. When the instruction is sourcing any of the registers that are being written by these instructions, you can stall this right away. Or you can be a little bit more intelligent, right? You can stall the dependent instruction only when necessary. For example, this instruction may actually need the value that's produced by a later instruction, but that value doesn't get written into the register file until the write-back stage. Right? Instead, what you can do is you can do the bypassing of the value, because the value may be available right away. The next instruction, let's say this instruction is dependent on this add over here. Add that's producing R3, and this another add that's consuming R3. Well, the value actually is available right after the addition is done. If we could actually design circuitry that detects this and that takes the result of the ALU and forwards it back over here, and we will see this. I know I made a mess over here, but forwards it over here. Now you don't need to stall the next add. You don't need to wait. You don't need to stop this add here until the add that's producing R3 writes to the register file. You can actually do the adds back to back. The realization is that this ALU result is available right away, but it's not written into the register file. You don't need to wait until it's written into the register file. And there may be other options that we may discuss. So in the next lecture, we'll pick up with data forwarding. But I gave you the basic idea of data forwarding, bypassing. In the next lecture, we'll go into the detail of how to implement this data forwarding in a pipeline machine. Okay.